So it's my pleasure to welcome Dr. Ram Sriharsha. He's the CTO of Pinecone, which is the leading company in the space of vector databases. At Pinecone, Ram is responsible for overseeing the company's technical direction in both engineering and research. Prior to joining Pinecone, he held numerous senior positions at some of the most well-known companies in the tech industry. Most recently, he was VP of Engineering at Splunk, and before that, the product and engineering lead at Databricks for their unified analytics platform for genomics. And even before that, a principal research scientist at Yahoo. Holds a PhD in physics from the University of Maryland. Ram, it's my pleasure to welcome you. Please.
Thanks for having me, Mayur. Hope you all can hear me.
Yes.
I've prepared a few slides. I wasn't 100% sure what level I should target them at. So I want to make it as interactive as possible. It should probably amount to about 30 minutes or so of slides, but please feel free to interrupt anywhere and at any time. With that said, I wanted to talk to you a little bit about this idea that knowledgeable models are models that actually can work with accurate, relevant knowledge, need to combine retrieval with generation. Okay, this will also be an introduction to what people commonly call RAG, and I'll walk you through some of the problems, the challenges, and how it's solved. Cool. So I won't really talk about language models themselves too much here, assuming that you all have a background in them. I will, though, talk about some challenges. So for if you work with language models, you know that first of all, they're very expensive to train. Training GPT-4, not only expensive in terms of time, expensive in terms of cost and infrastructure as well, right? And because training these new models takes a long time, they have a knowledge cutoff. So GPT-4o, I think, has a knowledge cutoff of October 2023. So anything beyond that, it needs to really know by either the context that you provide or by real-time search. These language models also have finite context windows. I'll get into context windows specifically in a bit more detail, but there are some architectural limitations of language models. What that means is that their information is stale, and there is only limited ways to pass information. Second, even if you provide the right information, sometimes they'll provide you the wrong answer, and they'll provide you the incorrect answer confidently. That's what we call hallucination. And sometimes they may not even consider the context that you provide. Both of these you can put them under the umbrella of hallucination. Now, sometimes they may provide you the right answer, but they may not be able to attribute that answer correctly. So attribution is important in any real world scenario where you kind of want to know where that piece of information came from. And lastly, more important in the real world, is the ability to redact information, the ability to determine who gets access to what piece of information. And this is extremely hard in language models because language models today store the world knowledge and private knowledge, if you were to train them, in their model parameters. So it's very hard to disentangle that with the information they need for language understanding in general. Any questions so far? Also, are you able to hear me properly?
Yes.
Perfect. So, of course, these are well known for the last few years. And there are a few ways people have been thinking about solving this problem. One is model fine-tuning. So if you have private data, you could actually fine-tune the model. Well-known language model providers provide endpoints where you can actually do this. That reduces the complexity of dealing with infrastructure and things like that. But it's still pretty expensive to do fine-tuning. And fine-tuning has the same problem, that it's expensive to do continual fine-tuning. As new data comes in, as new knowledge comes in, you kind of need to keep this model up to date. Secondly, redacting information is just as hard. It is, however, useful for scenarios where you want to embed the knowledge itself into the model. So, for example, if you're building a coding assistant, for example, and you want the assistant to provide a style of code that maybe your organization is more adapted to, and you want to enforce that, the best way to do that would actually be to fine-tune. Okay. So there are scenarios where you clearly want to fine tune, but a lot of the problems I talked about before don't go away with fine tuning. People have also explored using long context windows, and I'll talk about this in a bit more detail. Now, long context windows, in my opinion, and I think in general, are not mutually exclusive with RAG. They're actually useful in conjunction with RAG. However, there is a limit to how much of a long context that is actually useful. And finally, RAG, which will be the topic of part of this, the rest of the talk, is RAG offers a promising solution that's both flexible, that solves the data management challenges, and is also in some sense scalable. And I will kind of lead you through that, and towards the very end, maybe even tease out why I think RAG is actually a step in a broader direction. Now, that said, if you really only had to take away a few things, this would be the takeaway, which is there are challenges with language models, and some of these challenges are fundamental, and some of the fundamental challenges have a good chance of being removed by techniques that look like RAG. Okay. Cool. So before that, I want to briefly introduce in-context learning, because that's kind of what makes both long context windows as well as RAG useful and functional. So in-context learning is this ability that large language models have to perform downstream tasks by conditioning on a prompt of input-output examples, which is what we call context. Okay, and this happens during query time. So there is no training involved here. There is no modification to the model parameters that happen. And quite a few practical use cases today use in-context learning to adapt off-the-shelf language models to interesting tasks. Okay. Now, what sort of learning is actually happening? What is really happening here, right? There is quite a few experiments that have been run on trying to understand in-context learning and what is causing it. Now, there is no complete answer to this, but I will just maybe mention a few results and what they seem to suggest. First of all, clearly supervised learning is not happening. And one result that talks of one experiment that kind of showcases that is when when you change basically so imagine that you have input-output examples, and the output examples have gold labels, and you replace the gold labels with random labels. You would expect that if some sort of supervised learning was happening, then you would see the consequence of that in loss. You don't actually see that. So in this example, the what do you call it? Orange and red bars indicate the gold labels and replacement with random labels. And you see that the F1 score doesn't drop too much. Okay? And it's significantly better in either case than no in-context learning at all. There is another paper that kind of illustrates what might be happening with in-context learning a little bit better. This is a paper from Anthropic, which showcases that this idea that there is this concept of induction heads. So there are attention heads that combine together. So there's circuits that combine attention heads together in different layers. And what these do is they learn certain patterns. And they're learning patterns that are, in some sense more generic. So for example, let's just say B repeats after A, and this is a pattern. Then this combination of induction heads, or this sort of a circuit, will learn that pattern regardless of what A and B are. Okay. So, and that's useful because now when you do in-context learning, you're no longer relying on the pre-trained A's and B's and things like that, and you can adapt to this downstream task much better. Okay. It looks like a very specific sort of learning, a very specific sort of pattern recognition, but it seems to, at least in quite a few experiments, seems to suggest that this could be the dominant way in-context learning happens. So what these two kind of graphs show here are in the single layer attention-only kind of setting. There is really no in-context learning happening because, as you see, more and more, the more and more you train, the change in loss is not does not have some sort of a phase transition. Okay? Whereas in 2 and 3 layers, you do start seeing phase transitions. And you start seeing phase transitions right around the times when induction heads start forming. So it seems to be correlated to the existence of these heads. Okay. Okay, cool. So that's a very brief explanation of what might be happening around in context learning and why language models actually in context learn. But regardless, they do have this capability, and now we can leverage that capability, which means there is one simple way that we could think about providing knowledge to language models, which is just take the whole corpus and send it as a long context to the model. There are a few problems with this. So first of all, it is quite expensive. Now, I just took these numbers from GPT-4o, I think. And if you took the collected works of Shakespeare, that's about somewhere around 1 million tokens. This would cost you about $2.50 per query. Okay, and that's 3 orders of magnitude more than what you would pay for inference, right? Pay for generation for some question that you would ask about Shakespeare or the works of Shakespeare. So this clearly orders of magnitude more expensive. It is also going to be slow because passing in 1.2 million tokens for every query is clearly slow and inefficient. Also, many language models don't allow you to do this today because, for example, even GPT-4o has only about 128K token window, okay? Token size window. But more importantly, this actually does not work. So fundamentally, this actually doesn't work. So why don't really long contexts work? So there is a paper that talks about what happens with long contexts. This is a paper that's a couple of years old. The graph that I pulled here is on the left is from that paper. On the right is an experiment that we ran at Pinecone on a data set that's called NQ. It's a popular information retrieval data set. So both kind of align very, very well with this idea that language models tend to learn things that are, or tend to use the context better if you provide information closer to the head of the context rather than the tail or the middle. So you can see that in the graph on the left, you can see that the accuracy as a function of position degrades as you start placing data in the middle. Okay. Similarly, on the right, you see that in this experiment, what we did was we do the traditional F1 score and as a function of number of tokens, but we place irrelevant documents, what we call the top K distractors versus the bottom K distractors. And as we start placing distractors at the top versus the bottom, you can see that the F1 score drops dramatically in terms of placing the distractors at the top, right? So as you can see, the blue line or the blue curve is dramatically sharper and falls faster than the red curve. This again kind of confirms our hypothesis that in terms of long context windows, there is a point of diminishing returns with where you place your documents in the context. Okay. But of course, that's a challenge because you don't know you don't know what part of that context is useful in the first place. One other issue you see is, this is, I think, a result from the paper Ruler. It's a similar highlights a similar issue, which is you could have these really large context models. So Gemini Pro allows you to have 1 billion context length. GPT-4 has 128K, as I mentioned. Quite a few of these language models today start allowing you to have large context lengths, but you can ask the question, is this context length actually effective? And what they show is that in all cases, no, there is an effective context length beyond which the context is actually not useful. And most often this effective context length is somewhere around 32K to 64K, depending on the model, right? What they also show, which is pretty interesting, is, okay, these are experimental results, but can we think about why this is happening? Right? What is the framework by which we can think about whether this is something that's going to happen or continue to happen, or is this something like will get solved very easily, right? So first of all, what they find is that going back to the observations we just made before, they find that these sort of language models with long contexts are not robust to the needle in the haystack, which is basically you place a kind of ask a question about a UUID or something that's very unique and put it in somewhere in this context, they'll have a hard time extracting it. Second, as we discussed before, they can't really deal with distractors well. The third issue that they see that we see is incomplete retrieval of information. So they may actually tend to some parts of the context, but they won't retrieve enough of it. And often they end up actually copying from context. So instead of generalizing from it, they're really just copying from the context. They also have hard time tracking entities, for example, within the context. So if you have to track an entity across multiple parts of the context, that's harder. And finally, in all these cases, you see frequent hallucination with long context. So there are a few fundamental problems that they find, apart from empirical evidence, that long context is really not the solution. Okay. So what is the solution? So the same paper that talks about the fact that long context is not really the solution also looked at the following problem, which is instead of placing random stuff in the context, or instead of giving the language model everything, can I just give it the most relevant pieces of information, right? And what happens? So first of all, they find that if you just give it everything, there is a saturation in terms of what quality you can get out of the language models, and pretty much all of the language models start saturating. Those are the curves in the bottom. But if you combine language models with this sort of retrieval, where you're giving it just the relevant information, then you don't saturate for a long time. Okay. Secondly, this is on the right, an experiment that we ran, where we took existing. This was about probably 6 to 7 months back. So we didn't have, I think, GPT-4o here, but we had GPT-4 Turbo, GPT 3.5, Mixtral, Llama, and so on. And what we wanted to do was figure out if we took any of these language models and added retrieval as a step. So we are passing it just the relevant information that it needs to answer queries. What happens to the faithfulness of the model? What we see, interestingly, first of all, is that every model's faithfulness improves. What we see, even more interestingly, is that they all kind of reach roughly the same level. Okay. So this is that's interesting. But there's also one more interesting observation we can make, which is clearly by giving only the relevant context to a language model, your cost per number of tokens is definitely going to be lower. And likewise, we find that the accuracy for the number of tokens is definitely lower. Sorry, higher. So you get higher accuracy and lower cost for the same number of, higher accuracy for the same number of tokens, or lower cost for, for more tokens, because with more tokens in the context versus more tokens in a retrieval oriented database, the cost of the database is far smaller than cost of maintaining the context. Okay. This I mentioned very briefly. This experiment is really taking the web corpus, which is data that the models have been trained on already. And for queries on the web corpus, simply use retrieval to extract the relevant information and give it as context to the models for them to actually generate an answer. So you see that not only does every model's performance improve, but they all start converging. So in some sense, retrieval actually acts as a great equalizer. You can have cheaper models, smaller models, achieve better quality and better groundedness and better faithfulness for knowledge-intensive tasks without having to pay for the cost of training these big models and so on. And this is not just theoretical. So if you go to Pinecone today, we have something that's called the Assistant, where you can actually dump unstructured PDF documents and text documents and so on. And all you do is just ask a question. You can ask a question about what is Coca-Cola's, FY21 COGS divided by margin, something like that, right? COGS as a percentage of margin. Now, this data set is what's called finance bench. It's a standard data set that we use in information retrieval. And you can see that in this case, the answer was precise, correct. The 39.7% is actually correct. Not only is it correct, it had to pull information from different parts of these documents. And by the way, the corpus has thousands of PDFs. Each PDF is several hundreds of pages. So we're talking about a fairly large corpus of data through which you had to sift through and figure out the pieces of information required to answer this question. And not only that, you had to now put it together to come up with a calculation and finally reference it. Okay. So this is what you can do with something like RAG. Okay. What you can also do with RAG is refrain from answering a question for which there is no supporting evidence. Now, this is where models tend to hallucinate. So you can ask a model a question, and if I were to ask this GPT-4 this question, it'll actually give me an answer. But in the case of Pinecone Weather Assistant, for example, you can ask it this question, and if it's not supported in the data that it has, it won't give you an answer. Okay. So you can do things like this. Similarly, you can delete the document, and now, if it was able to previously answer a question about the document, it no longer will be, because it doesn't have that data anymore. So all of the data management challenges and so on become simplified with this sort of structure. Okay. So these are things that work in practice. Now I'm going to talk a little bit about how that happens. So I'm going to pause here. I thought there was a question. Was there a question? Okay, maybe I'll continue. So how exactly does this work? How do we combine retrieval with generation? So first of all, if you look at what I did there, I typed a query, which is what's Coca-Cola's FY 2021 COGS as a percentage of margin, right? Now, somehow I had to take that query and go to the set of documents, perform what's called retrieval. And in the process of retrieval, I had to get a set of passages that are relevant to the question I asked. And then I had to read those passages, synthesize something out of it, and then put it into context for generation. And then the language model now has the information that it lacked before. And then it uses that information in context to do learning and to actually answer the question. Was there a question?
All over the room, so it's picking up any whispering.
Okay, no worries. Cool. Okay, so first of all, before we can even answer that question, we first have to somehow take your documents and break them up. So we have to convert them into what's called chunks or passages, right? So there's some way we have to take unstructured documents and break them up so that the relevant pieces can be retrieved. Now, there is many ways to do this. I won't cover all of them, but I'll just kind of state it as there is an umbrella of techniques called chunking. Fixed size chunking is obvious. You just chunk it in a set of fixed size of tokens. Now, obviously, the problem with doing that would be that if you're chunking it in some fixed sizes, you might miss complete sentences. You might not be paragraph aware and things like that. You can also chunk by doing something called context-aware chunking, which is instead of looking at each of these chunks in isolation, you can decorate it with some context around about the document itself. Now, all of these techniques have their plus and minuses, but in general, chunking is a fundamental step in being able to do this sort of retrieval. So if you want to actually retrieve information, and you want to retrieve information at a level of granularity on which you can act, you basically want to chunk first. So once you're chunked, so then what do you do? So now you have chunks and you have queries. How do you know what to retrieve, right? Now, there are many ways to do this. Even before embeddings, even before all of this, there was the classic keyword search, right? And what was keyword search doing? It was basically computing a score between a document and a query. So if you had a query, the query would contain keywords. Then you would compute something called the BM25 score of that document, which you would compute by knowing the inverse document frequency of each of these terms, and then applying a formula like this. So this is roughly what happens in the keyword search engine. So now you get a score between a document and a query, and then you can rank by those scores and pick the documents that have the highest scores. So this is one way that you would determine which chunks are relevant to what queries. Now, this is great when the documents have a keyword match, but oftentimes documents don't have keyword matches. And then what you do is, for example, in this case of a query, here is a query where I have a query that says something like, do any large monkeys come from the jungles of Indonesia? And then there is a document that says orangutans are native to the rainforests of Indonesia and Malaysia. Now, there is only one keyword match here, which is really Indonesia. There aren't really any other significant keyword matches. So if I relied only on keyword matches, then this document would have been just about as important in BM25 terms as any other document having Indonesia in it, and clearly wouldn't have been picked up correctly. However, you can do what's called semantic learning, which is basically something called a cross encoder. And the cross encoder now looks at queries and documents and decides a score between this query and document. So one way to do this is to use a BERT model and a classifier on top of it. What you get is a score that's closer to 1 if this query is closer to the document in some sense, and further from 1 if the query is further from the document in some sense. So now you could imagine, given a corpus of documents and a query, you can just run this classification and then rank the results, just like you would have done in BM25, and then take the top few and say those are the relevant passages, right? You can do this, and in fact, this is what happens in a re-ranker. So if you're familiar with a re-ranker, that's kind of how it works, okay? The problem with re-rankers is re-rankers are expensive. So this particular operation takes a long time, and it's linear in the corpus. So if you have 1 million documents, you have to do this 1 million times, and each of these computations are actually expensive. So while this in theory works, this is usually reserved for post-retrieval step, where people re-rank the results of retrieval rather than for the retrieval step itself. Okay, so the problem was really the efficiency. Now, how do you solve that efficiency? So the efficiency problem is solved by, instead of using what's called a cross encoder, you can do a bi encoder, which is you can encode the document separately, you can encode the query separately, and then you can perform similarity search between queries and documents. So in this case, for example, I've taken the orangutans are native to the rainforests of Indonesia and Malaysia, I've tokenized it, computed embeddings, and you could do this in many ways. You could compute sparse embeddings out of it, you could compute dense embeddings out of it, and likewise, you would take your queries and then map it to the same space. Then what you're interested in terms of document query similarity is my document and query close to each other in the space. Okay. Now that's what leads us to vector databases in the first place. So in order to answer that question, which is once you've taken a vector embedding, put it somewhere, you have a query, the query is somewhere. Now the question that you have to answer is, in this space, give me all the candidate documents or chunks that are close to this query in this vector space. Okay. And that's exactly what a vector database does. Okay, so why a vector database in the first place? Why can't why can't we do it any other way? Now, there are lots of indexing schemes that traditional databases use. Usually, these indexing schemes break up space somehow and then allow you to bifurcate the search over it. A good example is R trees or KD trees and so on, B trees and things like that. None of those approaches actually work, because when you try to search for the nearest neighbors in a corpus in high dimension, by the way, high dimension because all of the BERT embeddings, for example, are 768 odd dimensional. Today, ADA2 embeddings are 1536 dimensional, and so on. So we are talking about pretty high dimensional search. And when you're doing high dimensional search, it turns out that most of the query volume, in other words, if you're doing nearest neighbor search on a unit cube in D dimensions, most of the points are kind of at the edge of this cube, which means you have to explore nearly the entire space in order to find the nearest points. So any sort of scheme that tries to divide up the space somehow is going to be highly inefficient. So you can't just take traditional databases and somehow kind of make them do this. So how do vector databases solve this problem? First of all, what they do is they don't provide exact nearest neighbor search. They provide approximate search. So this is the fundamental trade-off that vector databases expose for you, which is you could do bounded amount of work for queries and get a trade-off between cost or latency and recall. And of course, the more recall you need for certain queries, the more work you will do. But the whole job of a vector database is to try to do this as efficiently as possible. But there's always a fundamental trade-off in any vector database that you're trading off latency/cost for recall. And they do this, once you have this trade-off, you can exploit that by building new types of indexes that are optimized for search. Now, I won't go into too much detail on these indexes, but I'll give you like a very quick example, which directionally is correct. Now, today's vector databases use fairly complex indexing techniques and so on, but you will get a good mental model by picking something that's very simple. So if you just picked a graph-based indexing technique, the way it would work is that there is a phase in which a graph is being built. And this graph is the nearest neighborhood graph. So every point you add into the system, so think of each of these points as a row or a record in your database. And each of these points contains your embedding. Every time you get one of these records, you want to draw edges between that particular node and the closest nodes that it needs to know about. Once you have that, that's called a pre-processing phase, and the neighborhood graph is built. Now, during the query phase, when a query queue comes in, you start at a random node in this graph. And then you greedy search through this graph until you're stuck. So basically, you're just following the closest nodes from there on. And once you get to that point, you do a best first traversal from there. Okay. And you do a best first traversal until you find the top K matches. So in this example, you would kind of start somewhere, maybe start at a random point here, and then kind of just keep following edges that are putting you closer and closer to the query point, and then kind of get to this point. From here, the top K is determined by kind of best first traversal from here. Okay. Any questions so far? So now the key thing, of course, is that the whole reason why we built all those neighborhood graphs and things like that is so that there is always a path from here to here. That's one. Second is that now, hopefully, you're cutting down the number of nodes you need to traverse significantly in each of these steps. So overall, within maybe order 10, order 20 hops, you're at your closest neighbor, regardless of where you started. Now, this is where the sophistication around how these neighborhood graphs are built and so on comes in. Not only that, now you need to do index management, which is now, let's just say I have to delete a point. Maybe a record has to be deleted. Now, what do I do about it? Now, clearly, these sort of graphs cannot just be local neighborhood graphs, because if you just maintain local neighborhoods, you may not have connectivity or enough connectivity. So deleting one node could actually lead you to a disconnected graph, which by definition means you need to have long range edges and things like that. The moment you have long range edges, you could actually be doing a lot of work during deletion. So the real challenge becomes, how do you do as little work during deletion as possible while still maintaining the structure of the graph and so on, and not ending up with a lot of memory, a lot of space, and things like this. So there is a complex index management challenge that vector databases have to solve. Now, again, I'm giving you a flavor of this in a very, very simple setting. The real setting will be more complex than that, but I think it still intuitively gives you an idea. Even more importantly, most of the time you're never searching for, you're never searching for everything in the corpus. So you might be interested in, your query might be interested in dates that maybe documents that are more recent, maybe the last that have been written the last month, or maybe the documents that have been read in the last month, or what have you. So when you have that, typically the way you deal with this in databases is you apply a filter. If you apply a filter to vector search, you could actually end up in a very bad scenario because your filter could actually cause, because the filters and geometry are in some sense disentangled, you could end up with filtering with adversarial filters having to scan the whole space. Okay. So again, the problem here is that filters and geometric arrangement of data don't always go together. Filters and graph nearest neighborhood graph based arrangement of data don't always go together. But in any case, that's the job of the vector database to do. So your entire vector database's focus is on how do I take these embeddings, how do I rapidly update them, how do I rapidly update my index so that when a query comes in, I'm efficiently able to scan over as little data as possible to be able to surface the likely closest matches to this query. So that step is what we call retrieval. Once we have retrieval, we do what's called re-ranking. And re-ranking is where you now no longer just take the embeddings, but you actually have access to the documents themselves or chunks and the queries. And you do a a cross-encoder between query and documents. And so you're able to generate a final set of chunks to re-rank. Now we may take the top K of those chunks, and that's what becomes your context. Okay. So this summarizes what we discussed before, which is somehow you want to take your documents, you want to somehow convert them to passages, you want to take those queries, identify the right passages, put them into some context by reading it, and then give it to the language model. So far, what I've discussed is what's called frozen RAG. And frozen RAG is already pretty powerful. Okay. However, this is not the end state of RAG. So if you think about it, why do we call it frozen RAG? We call it frozen RAG because this completely separates generation from retrieval, right? So retrieval is happening upfront. There is a search query that comes in. You go to this database, you retrieve it, then you give it to the language model, and the language model generates something with it. And there is no feedback. And there is a disconnect between the retrieval and the generation steps. Now, you can definitely improve upon frozen RAG. In fact, the RAG paper that originally introduced this architecture isn't a frozen architecture. So if you look at the RAG paper's architecture, there is an end-to-end backpropagation through the retriever itself. And a lot of people today don't do this end-to-end backpropagation. So when people talk about RAG in the industry most often, near about most often, it is always frozen RAG. Now, or in other words, it's always like zero-shot retrieval augmented generation. That is already powerful, and that's kind of why people do that. Now, end-to-end backpropagation through the database is much harder, but this was the original design of the RAG papers. If you're reading up literature, for example, and you see retrieval augmented generation, this was the original architecture. I want to take a step back here. By the way, I will pause and kind of take questions since I've been talking for the most part here. So I want to maybe talk less. Before I do that, though, I do want to maybe say one thing about RAG. So we started thinking about RAG, at least in this presentation, the way I kind of led you to RAG was starting with language models, looking at large context and saying, oh, large context is great, but it has some challenges. So what do we do about it? We somehow need a way to give it information. And yes, there is this whole body of literature and body of work called retrieval. Let's just use retrieval to provide relevant information to language models. And the simplest way to do it is frozen RAG, where you just literally just do retrieval first from your queries, get the information, massage it together, give it to a language model in its context, and let it do its thing. So it seemed like a very tactical way of solving this problem. But there's actually something more general going on. The more general principle is language models need the ability to externalize their world information. So they already have world knowledge. They need a way to put it somewhere, as well as do the same thing for private knowledge. Okay. This allows them to deal with new knowledge easier. This allows them to deal with redacting information easier, and so on. So once you think about the life cycle of information, they need this ability to externalize that knowledge. Secondly, language models are already creating embeddings. They're already attending to embeddings. So they already are in some sense using vector search in a very loose term. And in particular, vector search captures semantic meaning extremely well. So it can not only capture semantic meaning extremely well, the vector space is rich enough to summarize efficiently large amounts of information. Given both of this, it makes a lot of sense for language models to increasingly leverage vector DBs. So I view RAG as really just a first step in that direction. And in fact, a couple of years after the RAG paper, there was a paper that talks about this idea. It's called a memorizing transformer. And the basic idea is that just like you have attention heads in transformers and so on, you can actually have a nearest neighbor lookup head, a head that basically pays attention, not over the embeddings in memory and things like that, but over embeddings in vector databases. So this is just the first paper in a line of papers that have talked about this idea. To me, it's a very promising direction, and I think that in the future, you're going to see language models that directly combine vector DBs to essentially externalize a good fraction of their memory. Okay. So I'm going to stop here. Hopefully this was useful. I want to first gauge the, was this useful? Was this not useful? And then maybe take questions.
So we have we have less than 15 minutes of Ram's time. He has to leave at 2:45. So are there any questions from the audience here? Okay, yeah, how about
do I just speak here? Yeah, am I audible if I speak like this?
Yes.
Okay, so yeah, thank you for your presentation. I think you mentioned interesting engineering problems related to similarity search regarding vector databases, but I was wondering if you experienced or encountered cases where there were conflicting information in the retrieved documents, and how do you deal with those cases? So for example, you could have like 3 to 5 documents retrieved from the vector database, which may have conflicting information. And maybe it matters more in the case where factuality is really important. Is there any auxiliary prioritization techniques to, give more focus on like one particular document over the other than the embeddings itself?
Yeah, this is a great question. I think often these sort of things you have to do with some sort of either training or like prompting, meaning the retrieval portion of the stack itself doesn't care about factuality. It just cares about the fact that this information was present in some corpus. You see what I'm saying? So from its point of view, it doesn't have any further information.
Okay.
But the person who knows about factuality is the end user, right? Or like some other kind of human labeler or someone like that. So I think this would have to involve some sort of a human in the loop labeling training sort of process. That, by the way, when I say training, it could even be in context prompting and things like this. So there has to be something outside of this flow that yeah, you're 100% right. This doesn't answer that question at all.
Okay. So right now, pretty much vector database is just the embeddings and like no other information other than the embeddings.
I mean, they do have some other information, but they use that more for filtering and things like that and data management. Likewise, re-rankers do contain the documents themselves, but none of them actually contain the information about the factuality of the document, right? Like, so that's a separate thing. What you can do, however, is you can actually come up with metrics. You can have, if there is a way to come up with metrics around factuality and so on, you could use that to tune systems. And that's the way to, I think you would have to solve this problem.
Okay, understood. And then like as an extension to that question, there might be some information that may change over time. Is there also like temporal information that researchers utilize when they're retrieving information from the database? So for example, certain knowledge about the world may change over time, and you have like multiple information about the same knowledge.
Yes. Yes. So one way people do this in vector databases is through filtering. So I mentioned filters, right? A filter you
Right.
could have is that give me just the last month of data, or basically, uh, in re-ranking, you could re-rank the fresher data
Okay.
higher than the staler data. You see what I'm saying? Like there are things that people do in order to rank and weight more recent documents higher than less recent ones and so on.
Okay. Okay. Understood. Thank you so much.
Uh, I think there are a couple of questions on the chat. Let me see if I can go back and read. So I think Kwan, your question was, as far as I know, retrieving or searching with RAG is generally quick, but the re-ranking step tends to increase latency. Yes. Do you have suggestions for speeding up re-ranking? It's a great question. So we actually have spent quite a bit of time working on re-rankers themselves. So in fact, one of the reasons why, like I mentioned, the whole bi-encoder architecture exists just because re-rankers are slow, and just re-ranking the whole corpus is completely infeasible. What people typically do is they take maybe a few thousand passages and so on, and then you would re-rank that. And you just need your re-ranker to be fast for that. There are fast re-rankers available. So there are re-rankers today that are actually for that budget. Maybe if you're re-ranking a few thousand passages and so on, you could do that in a few milliseconds today. So this is a actively researched area where you can actually do much better, primarily because the re-rankers that do this tend to be smaller models, and smaller models that are trained well can actually do the job. So long answer to your question is yes, re-ranking can be sped up. I can maybe offline share with Mayur some techniques for doing this and some papers that have done this, and even some models that exist in practice that are pretty good. Lynn's question was, how can we evaluate retrieval performance? So retrieval itself, it's easier to evaluate because in the case of retrieval, you're looking at information retrieval metrics, right? So you have a query and you have a document, and you can use standard information retrieval metrics to do this. What people tend to do these days is use an LLM itself as a judge. So you take a much more powerful LLM, give it the document and ask it to generate some questions about it, and then you feed those questions to this RAG sort of pipeline, and then now you can check whether the RAG pipeline is giving you the right documents and so on. So you could do this without even labeling, by just using a language model to do this. Now that's not going to be perfect. It's better than nothing, but language models obviously are good at looking at short pieces of text and maybe a document and coming up with questions that may not generally match the sort of questions that humans come up with. Secondly, their ability to come up with questions on complex multi-document, multi-reasoning, multi-hop reasoning questions and so on is very limited. That said, this is usually a good start. Does that make sense? And by the way, if you go to Pinecone today, we do offer a API for what we call evals, which allows you to evaluate any RAG pipeline. And today we do that with specific metrics we expose and specific labeling techniques that we accept. But we are very soon going to release something that's completely unsupervised as well. So, and that does something roughly similar to what I said. What do you consider as the most important open research problem in RAG? I think the most important open research problem in RAG is the last slide that I just mentioned, which is I think most of the community is working on frozen RAG, or like pretty complex ways of using frozen RAG to generalize to other domains and things like this, because there is no good architecture right now that combines language models with vector DBs. There is some promising work here and there, but nothing that is actually made into a production system and something that actually works. If that is solved, I think that opens up a lot of things, a lot of possibilities. So to me, that's the biggest open research problem in RAG. Yeah. So I think Jason's question, I hope I'm pronouncing your name right, is suppose we retrieved 5 documents. How do we know how much improvement to LLM each of the retrieved documents brings. There's a few ways you could do this. So one thing you could do is actually give it documents in sequence, right? Or give it remove a document and see what happens. Sometimes we actually interchange the position of the document because, as I told you, the language models tend to have some biases in terms of where they pay attention to. So you can actually switch the order and see if that improves the situation. This is roughly how you figure it out. Does that make sense?
Are there any questions from here?
Sorry, Mayur, I didn't catch it.
A quick question. Can you comment on what you see as the most successful use case today in enterprise using RAG?
Yeah, I mean, there is a lot of use cases, whether it is customer support tickets being automatically answered by RAG systems that basically reduce your customer success burden, which in fact we use RAG for that even within Pinecone, right? Whether it is searching for information in your knowledge base and making it easy for people to search. RAG is very powerful for search, right? It's a better search than semantic search, the better search than kind of most other forms of search out there. Legal tech firms use RAG through the sort of infrastructure we provide and so on to basically pull up court cases that are similar to something that they are working on, and to be able to easily manage that sort of information and pull it from a large corpus of legal documents and so on. So there's a lot of use cases where this is highly successful. The main problem with not just with RAG, with even language models, is that unless you can reduce the probability of hallucination to zero, there are many use cases that you cannot even touch today, right? And I think if anything, that's probably the most important set of problems to solve, the ones that actually reduce hallucinations and the lack of groundedness to near about zero, to the point where you can confidently use them for high value use cases in industries where the tolerance to probabilistic answers is nearly nil. And this, I think, requires some fundamental advances. And then that's one of the reasons why I'm excited about language models that work much more closely with vector DBs, because you want tighter control over what models actually know and how they attribute.
One more question. So can you comment on other kinds of data stored in vector databases besides text? I'm especially curious about.
Yeah. So nothing in here is specific to text, to be honest. So you could do the same thing for images. You could do the same thing for multimodal data. You could have text and images, and you can actually represent them in a single vector space. So as long as you can do that, you can actually create embeddings and dump them into vector DB. And then you can search that space both by text or by images. So you can do multimodal search. So nothing really is specific to text here. That said, that vector databases are typically used in conjunction with, so vector databases are great for unstructured data, and they're great for text, images, and things like this that are nearly impossible to handle otherwise. For example, in the demo that or at least in this slide that I showed, nothing in here was actually easy to parse. So this information in here, finance bench, is all raw PDFs. So somehow you have to go look at a raw PDF and extract information out of it, convert them into embeddings, and kind of then structure them. The fact that you can do all of that without having a human somehow do parsing and figure out exactly what is a table, exactly how the table is laid out, exactly, for example, this information comes from some table on God knows what page. All of this stuff previously would have been nearly impossible to extract. With vector embeddings and with this sort of way of dealing with unstructured data, you can extract all this now, right? However, there are also cases where in RAG and in general in search, you still need some structured information extracted in some structured way. So you would always complement a vector database with some sort of structured retrieval. Make sense?
Okay, we have reached the limit of time that Ram has been available. So let's thank him once more.
Thank you so much. Hope this was useful. It was hard for me to tell when I was preparing the slides what level I should prepare it at, but hopefully it was helpful.
Yes, this was very helpful. Thank you very much.
Thanks so much.